What's going on, guys? Welcome to Let There Be Math again, and in today's video we're going to continue with the statement that we did in the previous video, and it is that whenever you have a function such as 1 over x, if we were to apply the regular formula we have been applying so far, which is essentially x to some power of n dx equals to x n plus 1 divided by n plus 1 plus some constant c. If we were to set n equals to minus 1, we run into an issue, and it is that in the denominator we're going to end up with a 0. And we discussed this very briefly in the previous video, but now we can elaborate on why this is an issue here and why we can't define this particular case for n equals to minus 1 using the same formula. Now if we look at the function 1 over x, and if we plot it on a set of axes, so we have x and y over here, essentially we know this is going to look like this. So we have a function that goes to infinity at the point 0, so it's essentially just a discontinuous function at 0. And it also looks like this. So the function approaches both positive infinity and negative infinity at the point 0. Now what this implies is that we can't really define this using this particular function because we get an undefined quantity, essentially something that blows up or goes to infinity. So how are we going to be able to find the integral for this particular function? We're going to use the fact that when we look at the function natural log of x and we try to differentiate that, we're going to use the fact that this is going to be equal to 1 over x. Okay, so we know from differential calculus that this is the case, because whenever you're trying to differentiate any function that consists of the natural log of some function f of x, the derivative of that is going to be equal to the derivative of the function with respect to x divided by the function f of x itself. Okay, so we have this well-known result, and we know, okay, if we want to go back from this particular function, we should just say we're going to define the integral as just the natural log of x. So in general, for any type of function of this form, we're going to define it as the natural log of x plus the constant c. Now we should be a bit careful with that definition, and it is that we know, for example, that x must be strictly a positive quantity, and it must not be 0 either, because that's going to make this go to infinity in the negative direction. So of course we're only going to treat the values of x which are going to be greater than 0. Now in some textbooks you might find that people write this down as the absolute value of x. Now that doesn't mean that we're differentiating the natural log of an absolute value. It's simply done for the formality of saying we know that x must be a positive quantity, so we're just going to restrict that to this set of values. Now this has an important consequence, because it means that when we're looking at a function such as 1 divided by ax plus b, we know that since this has the form of a binomial in the denominator, we can also write this down as the integral of ax plus b to the power of minus 1. And as we saw in the previous video, we were dealing with functions that have binomials to some power, and we found that we could apply a very similar formula like this one. We're just going to increase the power by 1, and then we're going to divide the function by the power n plus 1. But this function is going to give us the same trouble that the function above is giving us. We're going to end up dividing by 0, which is going to make this an undefined quantity. So how can we make sure that this actually gives us something that we can deal with? Well, if you think about what this function actually is, what we can do is we can simply think of this in the following way. So suppose we wanted to differentiate the function, and I should probably just write down over here. We have the function natural log of ax plus b. We're going to differentiate that using the regular rules of differentiation we have been exploring so far. And what this is going to do is, well, we're going to apply this formula. We're going to differentiate the function inside the argument. That's going to give us just the constant a. And now we're going to divide that by the argument itself, which is going to become ax plus b. Now, if you look at this function, it looks quite similar to what we have over here, except for this a constant at the front. So all we need to do to get back from this to that result over here is we're going to have to manipulate this in such a way that we get it exactly in this form. So one way to do that is we're going to have an a at the top, and at the same time we're going to place an a in the denominator. Now what that's going to do is, well, we know that this is the same as this quantity because that a cancels out. However, because we already know what this portion of the function represents, we can now define this as the following integral. This is going to be equal to 1 over a, which is just a constant at the front, and this whole thing is just going to go back to that natural log function. So now we're going to write the natural log of ax plus b, and this is going to give us the answer we want. So now just add the constant c, and that's our integral. And now we can test that by differentiating that function, and we'll see that we get back to this expression. So we need to be a bit careful with some of the formulas we derive. They might be general for a lot of cases, but there might be exceptions to the rule. And this is a very important one because it essentially tells you that whenever the power is equal to -1, you need to define your integral in terms of a natural log, which is something that is a little bit strange, given all the things that we have been looking at so far are just power functions. Now, looking at all of these examples, you might actually look at this expression here and you might wonder, what if the integral is actually expressed in this particular form? What if we had an integral that looked like this? So let's just make some room for that. I'm gonna just rub this out very quickly. Now, what if we had an integral that is the derivative of some function divided by the function itself, dx? What would that be equal to? Well, since we're going in the opposite direction, what this implies is that we should actually get the natural log of whatever is in the denominator, right? So we're going to get natural log of the function f of x plus the constant c. So if we were to find any type of integral in which we can identify the numerator as being the derivative of the denominator in some way, we could also integrate that and get this general formula. So in the next video, we're going to explore a few examples on how we can apply this to our advantage, and we're going to see how that's a very useful way to actually look at integrals. We can look at the derivatives first and try to guess what the answer should look like based on the properties of the derivative. As always, if you guys would like to see more videos from Let There Be Math, don't forget to hit the subscribe button, and I will see you guys in the next video.